I was working on a project for unsupervised part discovery with Patrick and Björn Ommer in Heidelberg. So the motivation is quite straightforward. There has been a lot of work on unsupervised key point learning, for example, from Cheng, Jakob, and Lorenz. And what we saw is that those mostly rely on some parametric shape model, mostly Gaussians. And that's quite limiting in the shapes you can represent. So we thought, okay, can we do this a little bit differently? This is how those models compared on the deep fashion data set. And now the question is, because when you relax this shape assumption and say, okay, we allow non-parametric shapes, then the question is quite obvious, how well do they perform for segmentation? And so what we did, basically, we took those key point models and instead of taking the key points for evaluation, we evaluated for the segmentation task. And this is not quite nice. And we had an idea, which I'm going to describe later, which gets us a little bit closer to something that resembles the segmentation. Yeah, so just remove the parametric shape model. That sounds pretty easy, but it's actually not that easy. Simple is still hard. Yeah, that's something really nice to say in this case. So how did we try to do this? So the high level idea was we are looking for something that makes the shape independent of how those parts look like. That's what I'm trying to explain here with the latent variable appearance. So basically what you can imagine when you have two people and the segmentation looks the same for their parts, but they can wear different outfits. So basically this is where you can see, okay, it must be independent of appearance. How to do this? For that, we basically had this idea that there was a lot of work on disentanglement recently, which is trying to factorize these the distribution into two independent components. And we thought, okay, maybe if we can achieve such a shape and appearance disentanglement, if we then somehow infer the segmentation just from this shape variable, then maybe if we do it correctly, we can get to the segmentation. This was the first high-level idea. The second high-level idea was, okay, now that we have this shape and appearance disentanglement, how exactly can we get something that looks like a segmentation? And for that, we thought, okay, if we just formulate a bunch of reasonable priors, for example, just a regularization, then we expected that we can achieve such we can learn the segmentation. And since we want to compare us to the unsupervised key point learning papers, we also have to do it unsupervised. And in that case, we just assume it's a generative model. Yeah, so how does it work? Basically, we have the same setup as for the unsupervised key point learning. So basically, you have two views. It's basically a multi-view method. And then we have a bottleneck for the shape. That's pi in our case, or pi for pose. You could think of that. And given the pose, we infer the segmentation. That's basically the decoder DS. And now that we have these two segmentations for the two views, what we basically do is we mask out each part, then infer the appearance again. That's the E alpha step, and recombine that in the other view. So that's pretty standard also from the key point learning papers. We just took that idea. And now that we have the segmentation with localized appearance, we just generate the image again. That's G at the end. And to get this off the ground, as I showed below, you need the right objective. So basically, it all works by reconstructing the image. That's just the generative part here. For the disentanglement, you need you need two additional objectives. The one is, yeah, you could describe it as a simple autoencoder, but it's not that simple. So that's the variational objective here with the KL between the posterior and the prior. And then we also have an adversarial term, which is similar to the mutual information estimation literature that has come up in the recently, and it's just a discriminator basically. And we have a reference for that in a second. For the mask or for the segmentation, yes, that's where the priors come in, and there's just two additional objectives. More details on this exactly. So what you can think of, the segmentation basically, if you look at it if you just look at how you could formulate something that looks like a segmentation in terms of a cost, basically what you would like is the segmentation to be smooth. Why is that? Well, if you look at within the region or within the domain where the segmentation is, the segment is, basically you don't really have a degree of how good it is. It's just one, at least if you look at it as a binary mask. And it's also, there are no islands within that. So basically it's a smooth connected region. And that's why we thought, okay, maybe we can just use a Gaussian Markov-Random field prior. In practice, this basically just means we add Gaussian noise and regularize. And then you can write down the fancy KL objective and do cool math, but that's all in the appendix. And the other regularization that gives us the second prize, what I explained also just right now, is that you want the segmentation to be hard. Basically, you have the part of the segmentation is either there or not. You really don't want to have, okay, this is only half at a certain pixel, the probability is only 0.5 that there's this part or not. So we can do this basically with the standards cross entropy or entropy. Basically, it doesn't matter which one you use. We found that it's basically the same with either of these. Yeah, so for the disentanglement, that's a lot more complicated. So what you do here basically is you have two encoders and you infer the one latent representation from one view and the other representation from the other view. So that's you have separated factors of variation in those representations, and then you assume, okay, the pose is independent given the appearance. Then basically this is the variational part, and then you also have these discriminator part, which is on the top right with the discriminator. If you want to look this up, this is quite complicated, and you can see below where we got this from. Yeah, so how does it work? So if you don't do any of the things I've mentioned, it's not going to work. And this is what I indicated with the skull here. If you just add the variational and the adversarial objective, that basically gives you this entanglement. That doesn't work either, because the priors are missing, which say, okay, this should look something like a connected region. If you add this Gaussian Markov-Random field, it gets better, but it's still really not smooth enough or hard enough, which is why we added the entropy regularization. So now we are at row 5, and if we now go back and remove one of the disentanglement objectives, it gets worse again. So basically, you need all of these objectives, otherwise it's not going to work. So yeah, so this is some cool results. And on deep fashion exercise and pin action. It works pretty nicely in some cases. Yeah, you can see here on pin action it's pretty hard because of the background clutter, because the generative model also has to somehow model these background variations. And we also tried it briefly on some bird data set. And that's also pretty promising, I think. Yeah, so what we can do the really classic transferring stuff, which is quite cool, I think, because you can you have like pixel perfect alignment with what you're transferring. And this is also what we use for quantitative evaluation. So we evaluated one on the segmentation task, obviously, because that's what we're doing. And for that, we see an improvement in most cases. And we also evaluated on shape consistency. This is what I just said. Since we have a pixel perfect mask now, we expect that the key points when you transfer the appearances onto another image, that this should preserve more information about the shape. Yeah, and that's it. So I hope I cut the time and not exceeded it. And let's have some fun now discussing.
Thank you very much for the nice talk. You were perfect in time. Well done.
Oh.
There's a few people, I guess, typing up on Discord. And while they type their question, I actually have one on my own. Sure. I'm not sure if you saw the talks on Monday, but Matthias Bethke talked about how CNNs are biased towards texture rather than structure. Yeah. Mm-hmm. And they use this style augmentation to essentially remove this bias. Would this also work/help in your case?
So this is a really interesting thing to discuss in general. We need a strong bias, because otherwise the factorization of the factors variation won't work. So the way we do it, I think it won't help, because we have this multi-view method. And that basically gives us a strong factorization of pose and shape and appearance already. On the question on texture bias, yeah, that's a problem actually. So you see on some data sets, the texture bias is just too strong, and you you would have to introduce a stronger bias that gets you towards the factorization that you need. In practice, so we found that you just should only apply the method when you know the data set allows it. So you could argue, okay, that's cherry picking the data, but actually it's more like preparing the data set to match the method. So yeah. You could also argue, okay, well, how can you make sure that you don't learn texture or appearance clustering? On the rebuttal, there were a lot of questions about that. Well, if that would be the case, you wouldn't have the consistency across instances, would you? So if people look differently, then it should factorize according to their clothes color, and not the arm should be consistently placed in the same position. So yeah, I think the method ultimately stands and falls with the disentanglement. And for this, I think so the method that we are building upon was developed by the second author of this paper. So it was more like, okay, we had this method, can we just apply something on top? Since disentanglement is still a work in progress, I think it makes sense to just see what's going, what will be possible in this direction.
Thanks for the detailed answer. There's one question on Discord. Really cool results. Were the comparisons supervised or unsupervised? Do you have a segmentation comparison to supervised methods?
Yeah, so the ground truth is dense pose. So dense pose is supervised. So I guess the answer is yes, we do have a segment comparison to supervised results, which is our ground truth. The first part of the question was?
Were the comparisons supervised or unsupervised?
Yeah, okay. So just to be clear on this, we compare against unsupervised key point methods. And for that, we infer the segmentations given the key points with a condition around the field. And the ground truth in all the cases is a supervised method dense pose.
Okay, thank you very much. And thanks for the great talk. The next talk will be by Jan-Hendrik Lange on the lifted multi-cut polytope for trees. Jan-Hendrik, if you could share your screen.
Yes, I think Sandro needs to, yeah, okay. Okay, thanks for the introduction. So this is joint work with Björn Andres from TU Dresden. And in this work, we are looking at the following problem. So suppose we have some tree structured data that we want to segment into meaningful groups. And we want to do this based on pairwise terms, theta uv, for distinct vertices uv in our tree. And the goal is to find now a segmentation, and the segmentation should be the one that minimizes a sum of those pairwise terms for each component. So those terms that are within each component. So and then we could get some solution like this. Now, so mathematically, again, we have a tree, and we have those pairwise real terms for each pair of distinct nodes in our tree. And now we encode a partition of our tree just as a binary labeling on the edges, where one stands for the edge is contained within some component. And then the problem that we want to solve is the following here. We're looking for the labeling that minimizes a sum of terms theta uv, and each term is counted if uv are within some component, that is if and only if they are connected by well, a path, the unique path indeed, of edges labeled 1. So PUV here stands for the unique path between the vertices u and v. Now this looks like a fairly general problem, and indeed in particular it includes the binary quadratic program if we select t to be a star. So in particular this problem is NP hard, and yeah, it includes actually a quite general class of programs which are the binary quadratic programs. But we are more interested in the case where the tree T is, well, far from being star-shaped. Now, if you want to solve this problem by integer linear programming, we first need a linearization of this problem. And this is what we do. So straightforward approach. We first substitute the product term by a variable yuv, and then also we make a change of variables. So we actually switch to x variables here, which are just 1 minus the y variables. So then we end up with an equivalent problem, which we call lifted multicut problem. So this is the same problem, just in x variables and as an integer linear program. And we have two sets of constraints, the so-called path constraints and the so-called cut constraints. These constraints ensure that xuv is 0 if and only if u and v are connected by a path of edges xe such that xe is 0. So, or in other words, xuv is 0 if and only if the corresponding product of y variables is 1. Okay, so this is the interlinear program, and so we are studying the feasible set of this problem. So which is called the lifted multicut polytope. This is just the convex hull of all integer vectors that satisfy the constraints. And you see a minimal example here on the right for just a tree consisting of 2 edges, and which introduces one additional quadratic term. Now, why is it called lifted multicut polytope? Well, the vertices are characteristic vectors of multicuts of the tree T that are lifted to the complete graph on V, as was defined by Honjakova et al. And hence the name of this object. Now, in order to solve this tree partition problem with integer linear programming, we need a strong relaxation of this object. So this is the focus of this work. Now, note that you obtain a naive convex relaxation P0 by simply dropping the integrality constraints in the definition of the lifted multicut polytope. But the point is that this is well, way too weak of an relaxation, so we need to figure out whether we can do something better. Now, first observation is that we can immediately obtain a stronger canonical relaxation, which is not so hard to see. So, and this is obtained by replacing the path and cut inequalities by the set of inequalities 1 and 2 depicted here. And those are defined for any triple of distinct vertices U, V, and W that are arranged as in the picture on the right. So U and V are just some arbitrary distinct vertices, and W is the first vertex on the path from U to V. And then, well, we have these two inequalities 1 and 2, which are valid. And it's easy to see that if you just take those inequalities and substitute them for the path and cut inequalities, you get a stronger relaxation P1. And yeah, this is also canonical in the sense that you define this purely based on these triples. Now, we want to know which of these inequalities are maximally strong. So in other words, which of these inequalities define facets of the lifted multicut polytope. And we show that inequality 1 defines a facet if and only if the distance of U and V is 2. And inequality 2 defines a facet if and only if V is a leaf. Now, in the case of T being a star, so these conditions are always true. So then there are always facets, and in the general case, they're not always true. And indeed, in the general case, there are only very few facets defined by these inequalities, and we need other inequalities that are maximally strong that define facets in the case where T is far from being a star. So this is what we looked at next. So we define this new class of facets, and those facets are induced by inequalities defined on 4 vertices, U, U prime, V, and V prime, that are again arranged as in the picture on the right. So U and V are some arbitrary vertices, and U prime is the first vertex in the direction of V on the path from U to V, and V prime, vice versa. So, and then we have this valid inequality 3 here, which we call intersection inequality. And we show that any intersection quality defines a facet of the lifted multicut polytope. So indeed, here we have a large class of facets that are obtained from this, well, path-like structure in our problem. Now, and yeah, so the main result in this work is that if we take it to the extreme, okay, it says G, it should be T. So if T is a path, so yeah, if it's just a chain of vertices, then the facets described by us yield a complete description of the lifted multicut polytope. So in this case, we can actually fully capture this object, which also implies that the problem is solvable in polynomial time. So the way we prove this is that we show that the system is totally dual integral. So basically the dual program is always integral. And so we apply a nice little trick, which is visualized here in the proof. That is, we introduce these additional terms that are depicted in green here. And then we can write the whole system as a system of only intersection inequalities and some equations. And then, well, it's just a technical trick to write the dual in a nicer way. And so I want to make a further remark. Actually, if T is a path, the problem actually admits an efficient reformulation as a choice path problem, or in other words, as a dynamic program. And well, the point here is that this dynamic programming program has quadratic size in the number of points n. So our polyhedral result basically makes a connection between the polyhedral geometry of the lifted multicast formulation and this combinatorial properties of other formulations. So with this, I would like to conclude. So we analyzed some facets of the lifted multicast polytope for trees. In particular, our results give a complete description of the polytope in the case that the tree is just a simple path. And insights into the polyhedral structure can accelerate interlinear programming methods in order to solve the problem. So with this, I thank you for your time, and I'm ready to take some questions.
Thank you very much for the interesting talk. Lynton had a question. Do you actually want to unmute yourself and ask yourself?
Okay, I can do so. My question was, can this be combined with graph neural networks to learn the costs and then somehow backpropagate through the algorithm?
Yes, so I mean there are approaches that combine learning with all kinds of optimization algorithms as part of the prediction pipeline. So there's recent works on using combinatorial routines, but there's also other works on linear programs and so on. So there is a way to combine these things.
I was wondering whether you, in your new formulation, whether you can actually show some tighter bounds on the error, or is the problem not approximable? So can you approximate it with some approximation factor, and does your method improve it, or?
So you mean in the general case for trees? So in the path case, we have a perfect description, right? So we can solve the problem exactly just by solving a linear program. This is what we show, and there are other ways of solving it. But in the general case, if it's a tree, well, then we have an imperfect description. And basically, the contribution here is that we derive some inequalities that are associated with paths, so which make the description stronger. But I mean, I don't know about the approximation qualities for this particular problem.
I mean, I was just wondering. Another question that I had in mind is, have you integrated this into some computer vision or / machine learning system?
No, we haven't. So this work is purely motivated by theory so far, because we were studying the lifted multicast polytope in a more general case. And basically, the underlying question was, what if we so generally you define it for any connected graph. So then the question was, okay, what happens if we restrict this graph to be minimally connected, so just a tree, and then you can actually make some more precise statements as shown here. So in the general case, it's even more complex. So but no, we haven't applied it to anything at this point.
I mean, it was not meant as a criticism. I like theoretical papers such as yours. I was just wondering whether you did something there, because I guess most people who attend this conference are more in practice.
Yeah, sure. I mean, so I was thinking, as I said, we didn't have a problem in mind, but I was just thinking generally, if so for the path case, for example, which would correspond. So it's a one-dimensional data. Your data is one-dimensional in a sense. So this would maybe correspond to some time series. So maybe you could apply it to some time series segmentation where you want to segment into an unknown number of segments and make precise cuts, and don't know how to do it other than having these pairwise terms. So this is maybe maybe something where you could apply it.
Okay, great. Thank you very much, and thanks for the great talk.
Sure.
Our next speaker, and excuse me if I'm butchering the name, is Lynton Ardizzone. If you could share your screen, correct my pronunciation of your name, and please take it away. You're currently muted.
Okay, now I should be there. Okay, thank you very much for the kind introduction. The name was very good. Yes, I'm speaking on conditional invertible neural networks for diverse image-to-image translation. So in a standard normalizing flow, you train this transformation from images or some other complex distribution to a latent space. And then you try to make the outputs follow a standard normal distribution. And this is done with a maximum likelihood loss. And we've seen this a few times in the last few days. Then at test time, you can sample from the latent distribution and invert the transformation to generate new images. And if you want to do this with a neural network, of course, you need an invertible neural network, or INN for short. So in our work, instead of the coupling blocks used in standard INNs, we use conditional coupling blocks. And that's just a way to inject conditioning information into this INN at each layer. So Vito Ferrari also had such conditional coupling blocks in his in the C flow that he showed on Monday in the invited talk, so I won't go into more details. But some of you might have already wondered on Monday, why don't you just use the conditioning directly, like this, for example? Well, the fact is, for image-to-image translation and most other tasks, this won't work, because this conditioning is injected at each layer, but it can't be processed in any way by the INN, just because it's not really part of the transformation itself. So just the raw pixel values of the condition are useless. You need to extract some higher level information first. Obviously, we saw one way how to do this on Monday in hint or C-flow, which are very similar methods. But in fact, there's an even simpler way to do this, which is our method that I'm going to show now. So what we do, in fact, is we just use the levels of a feature pyramid as these conditioning inputs for each layer. And this feature pyramid is just extracted by a standard feed-forward network. So I'll put VGG here as an example. Okay, and then this whole setup we call a conditional invertible neural network, or CINN for short. So if I want to train this as a conditional generative model, I do it in the following way. We start having the training data as pairs of the conditioning image on the left side here and the original image on the right. So then we first compute the feature pyramid and next run the INN while injecting these features. Then from the output of the INN, we compute the maximum likelihood loss in exactly the same way as standard normalizing flows. The important part then is that we can backpropagate this loss through the feature pyramid to update both the VGG and the INN with the same loss function. So in other words, both these components of the CINN can be trained jointly from scratch using just the maximum likelihood loss. If you then want to do conditional image generation at test time, you extract the features in the same way, but then inject them into the inverted INN. So by sampling Gaussian noise at the top here and running the INN backwards, we can do conditional image generation. Okay, then in the last 90 seconds, we can talk about what are the advantages of the CINN over other conditional generative models, such as conditional GANs specifically. So firstly, and Vito Ferrari already said this on Monday, all normalizing flow type models and the CINN specifically always generate the full diversity of the distribution. As you probably know, in C-GANs, diversity is still a problem, even if you use special regularization, and here this just happens naturally. So this example is for data-night generation. Then secondly, training with the maximum likelihood loss is simple, it's stable, and it's reproducible. Furthermore, the value of the loss sort of directly corresponds to the generative performance. So this helps in designing and comparing models, seeing if it's converged or overfitted, and so on. And this is also something that's not possible in GAN-based approaches. Then third, we have various theoretical results. For instance, we show that the extracted features will be maximally informative for the generative task, measured by the mutual information, even within the constraint of limited expressive power of this feature extraction. And we also show that if the expressive power is indeed large enough, the generated distribution will match the true distribution. So lastly, the invertibility allows for some intuitive ways to manipulate the outputs. So we show diverse image colorization as an example here, and there we combine the latent code of the images in the top row with this new condition on the bottom left in order to generate the images in the bottom row. And there's more examples in the paper of kind of manipulations you can do. Okay, thank you very much, and I'm looking forward to the questions and the discussion later.
Thank you very much for the great talk. One thing that I was wondering is how important is the feature extractor, and could it potentially be trained together with the INN, or does it need to be fixed in order for training to be stable?
Yeah, so as I said before, they are trained jointly, and you can also do it from scratch. So the feature extractor is very important, but it is trained together with the INN. And again, you only need this maximum likelihood loss, and you can backpropagate it through the feature pyramid to jointly train VGG. If you want to speed up convergence or something, you can of course use a pre-trained VGG, but I would always recommend to also train it jointly.
Do you know what the difference in performance is if you use the pre-trained VGG?
Pre-train and don't touch it, it still works okay. And I think we have this as an ablation. Yeah. If you don't have it at all and do this, then it fails completely. And we also have this as an ablation.
Yeah. Because in my experience, VGG actually, at least the first couple of layers are rather general features. So I would assume that you could do some fine-tuning just on the last few layers.
Yeah, it would probably work. As I said, we've done all these ablations. It also sort of works if you don't train it at all and leave it pre-trained, but you get best results if you train both jointly.
Okay, great. Yeah, thank you very much.
Thank you.
The next speaker is Håkon Hukkelås, and he will talk about image in-painting with learnable feature imputation. Please take it away.
Thank you for the introduction. I'm going to be talking about our work on image in-painting with generative adversarial network, and this is a joint work with Frank Lindseth and Rudolf Mester. And since this is a pretty short talk, I'm going to talk about our two main contributions, but in our paper we make three main contributions to stabilize the training of GANs for image in-painting. And going straight into it, we look into how you can handle missing values in convolutional neural networks. And just to be clear, we're looking into all the layers in a convolutional network, not only the input layer. If you apply a convolution on top of a region, when you have missing values, the output is going to be undefined. And if you impute these unknown values with either 0 or the mean, you're going to get visual artifacts in the resulting image. There's previous work that has looked into how you can normalize the output depending on the certainty of your input, but the previous work has either constrained themselves to a binary certainty, so you either know the value completely or it's completely unknown, or they have looked into learned operations such as gated convolution to learn this normalization, where they use about 50% of the parameters to compute this normalization factor. Instead, we look into if we can impute the input values of the convolution with an expected value. And we do this in a very simple manner. And the way we're doing it is that we define a certainty that is a real value number between 0 and 1 to represent if a pixel or a value is known or not. And then we do a simple interpolation between the known value and then an estimate. This estimate we find from spatially closed pixels, and this can be implemented as a depth-wise convolution that is weighted on the certainty. Note that here we're using a receptive field that is larger than the original convolution. If we look at our baseline network, which consists of a large set of standard convolutions, and replace each convolution with our imputed convolution, you can see that we get a significant better convergence rate on our network. And this is the learned perceptual image patch similarity, which is our main quantitative metric. Furthermore, we look into the generator architecture of our network. So from our previous work, we used a standard UNet architecture that was trained with progressive growing for the adversarial training to stabilize the training. What we noticed with this network is that when we increased the resolution to larger than 128 by 128, we got a large number of problems with converging this correctly, and the image quality was significantly degraded. If we zoom into the output of the decoder, and the way the final image is generated is that you have the final feature map, which is then convolved with a 1-by-1 convolution to a RGB image. And this can have problems when you're scaling up to larger generators or larger image sizes, because the gradient flow is going to be vanishing. Therefore, we are inspired by the multi-scale gradient GAN, and instead convert every feature map from every resolution of the decoder to RGB, and then sum up the contributions from each level. We couple this with a residual discriminator instead of using a standard discriminator with no residual connections, and this significantly stabilizes our training. To quantify our results, we take our baseline network and then incrementally include each contribution in our paper, and we can see an improvement in all of the metrics that we're reporting for each incremental improvement that we're adding. In our paper, we're showing a large set of qualitative samples, and we compare to current state of the art from the top conferences the last couple of years. And you can see that our network is able to impane the images quite well. Note that all of these examples are cherry-picked, and we encourage everybody to look into the supplementary material, as there are randomly selected samples there, and there's also samples selected by other authors. To conclude this very short talk, what we notice in our paper is that a very simple imputation scheme can improve final image quality compared to standard convolutions. And we're also one of the first papers that achieve state-of-the-art results with a pure adversarial training, where previous work has used some kind of handcrafted objective function, such as the L1 loss, to stabilize the adversarial training. And that's it for me. Thank you.
Thank you very much for the interesting talk. You said some of the examples that you showed were cherry-picked. Do you know how the failure cases look like?
So in our, so the examples where you're cherry-picking is actually showing some of the failure cases. And for both previous work and from our work, as you see on the right bottom screen here, the impaning can definitely be better. But the general case that we look at state of the art is that you're increasing the area that you're impaning. The network is starting to struggle both for our work and previous work as, yeah.
You have an idea of how much you can overpaint before it starts to break down? How large can the regions be that you mask out?
So this is mostly defined by the training set that we're selecting. From the gated convolution, we select a training set that has the maximum impaning you have is 25% of the image, I believe. Gated convolution, which define the data set, is struggling when you're increasing this semantic or the size of the area. However, in our work, we can see that the since our network has about 4 times the number of parameters, we are able to, when you get these very large regions of missing areas, we're improving the image quality compared to previous work.
Do you think the remaining problems are something that you could solve with having more training data?
No, I think the main problem with previous work is that optimizing a network with missing values is quite difficult, because at least when you get free-form image and painting, when the mask can be arbitrary, not in a fixed spot, the gradient flow through the network is going to be quite obstructed. Just because if you increase the masking region, the norm of the gradient is going to be smaller. And this is something we discuss in our talk about gradient penalties in adversarial training. So I don't think the training data set size is the problem. It's either the capacity of the model or how you model missing values in convolutional networks.
Yeah, thanks. Thank you very much for the good answers and the great talk. We come to the final speaker in this session, who is Patrick Wenzel, and he's going to talk about a cross-season data set for multi-weather SLAM and autonomous driving. Patrick, the floor is yours.
So thank you for the nice introduction and welcome everyone. It is my great pleasure to present our work today. In this work, we present 4 seasons, a cross-season dataset for multi-weather SLAM in autonomous driving. Existing datasets for autonomous driving have been an important factor for advancing the state-of-the-art in many computer vision algorithms. However, in terms of benchmarking long-term visual localization, these datasets are typically limited. To overcome these limitations, we feature conditional changes by providing multiple traversals of the same route. This results in large appearance variations caused by changes in weather and seasons. We do not only provide multiple traversals of the same route, however, we also provide large variations in the environment. This results in 9 different environments ranging, for example, from a monumental site to urban areas, to a countryside, and to a multi-level parking garage. Our main contribution is a cross-season and multi-weather dataset, which covers both diversity and complexity in the environment. Moreover, we provide up to centimeter accurate georeferenced 6 degrees of freedom poses. This results in accurate pixel-wise correspondences, which can be used for training deep learning methods. Our sensor setup consists of a custom stereo inertial sensor with a baseline of 30 centimeters. The sensor, together with the GNSS antenna, is mounted on a rigid roof rack. All sensors, cameras, and the IMU are triggered over an external clock generated by an FPGA. For the dataset, we have recorded more than 350 kilometers of sequences in 9 different scenarios. For each of the scenarios, we recorded multiple traverses of the same route at different lighting conditions, as well as different seasons. To obtain reference poses, we use our direct stereo visual inertial odometry algorithm. This leads to locally accurate 6 degrees of freedom poses and 3D landmarks, as shown on the right side for one of our sequences. However, if we revisit the same place again, you can see that the trajectory is drifting and the 3D reconstruction are not perfectly aligned. Therefore, as a post-processing technique, we perform post-graph optimization to compensate for the drift. This is achieved by doing loop closure detection and integrating RTK GNSS measurements to obtain up to centimeter accurate global positioning. As you now can see from the zoomed in views, the 3D reconstructions are well aligned and the drift is compensated. In detail, this can be seen here. The GNSS measurements are depicted in green, while the VIO poses are visualized in red. After the post-graph optimization, the drift in the trajectory is compensated. Also, the bus was reconstructed twice, and after the optimization, the 3D reconstruction of the bus is well aligned. Moreover, in challenging GNSS denied or combined indoor-outdoor environments, the GNSS positions are usually noisy or not available. Nevertheless, after the postgraph optimization, the trajectory is smooth and well aligned. This can also be observed in the vertical direction of this multi-level parking garage. To demonstrate the accuracy of the reference poses, we additionally visualize pixel-wise correspondences between images of different sequences. In these images, each same colored point corresponds to the same 3D world point. The points from one image can be projected into the other image based on the global reference poses. This shows that by using our approach, we can achieve up to pixel level accuracy. This is not only limited to two sequences. However, this can also be done for all traverses of the same environment. Therefore, points from an image from one sequence can be projected to many other images taken at different conditions. This is even possible if the points are projected to areas of the image without rich features, as for example, in the night image. The dataset will be released later this year. For more information, please visit our webpage. Now I would be happy to take any questions. Thank you very much.
Thank you very much for the interesting talk, and I can't wait to get my hands on the dataset. So yeah, I very much appreciate all the effort that go into creating and maintaining such datasets. I was wondering whether you ran some of the methods that work well on robot car seasons, CMU seasons, all those long-term localization datasets on your own dataset, and whether you observed that yours is more challenging for this type of methods or not.
Sorry for what kind of methods you are referring to exactly?
So there's this, you mentioned the robot car dataset, and there's
exactly,
this
yes.
Benchmark for localization on the different weather conditions and so on. And there's a couple of benchmark methods such as Paul-Eduard Salin's hierarchical localization and so on that work really well on those datasets. I was wondering how well they work on yours.
Okay, thanks for the question. I mean, first of all, the motivation behind our dataset is there are some datasets for visual localization, but our main motivation to create this dataset was that we can benchmark not only global image retrieval or local feature descriptors, but we also wanted to evaluate visual odometry and SLAM methods. So our dataset is a multi-purpose dataset which can be used for evaluating all of these algorithms, basically. To come to the second, to your question, we had run an ECCV workshop where we also had a challenge where we released subparts of the data set. So we released one sequence, and indeed also the method from Paul-Eduard Salin, HLOC, was evaluated on this data set, and it works surprisingly well. But I also have to say that we also have more challenging sequences which we didn't release now. So stay tuned for this.
Cool. Yeah, very much looking forward to this. Yeah, I think that concludes our session. Well, at least the live talk part. If you have any questions to the speakers, please join Discord and discuss it with them there in the channel. And yeah, with that, I thank you very much for watching, and a very special thanks to all the speakers for the great work you have done. Thank you very much, and see you all later. Bye-bye.
Thank you. Bye.